So the last time we gave the definitions of several modulation formats, and now I'd like to start moving from binary to M-ary in some intermediate steps. And I'd like to think now about the decision regions in signal space. And we'll start with some small sizes so we can get some basic concepts. So remember, binary examples in Chapter 3, we had antipodal signaling, we had on-off keying. We compared the two, we represented them in signal space, they're the same normalization on EB. We saw that the distance between on-off keying was smaller than the distance between symbols and antipodal signaling. And so we defined this separation of the two symbols, or this distance d, and we found the probability of error as a function of that d. It's the same analysis for both cases, but the D is different and the bit error rate was higher for on-off keying because it was missing this factor of 2. So we saw that antipodal signaling is really BPSK, so we've sort of already looked at BPSK, but how would we look at binary phase shift key, frequency shift keying? So what does the symbol space look like for binary frequency shift keying? Well, we know that these binary basis vectors are going to be exactly equal to the symbols themselves because the symbols are different frequencies which are orthogonal to one another. So that we know that essentially when we look at the signal space representation here, we're going to get one signal lying along the first basis vector and one signal lying along the second basis vector. And because they have the same energy, they're going to be at the same distance to the origin, and we can see these two x's here, which represent the representation in signal space. Again, this comes directly from it being orthogonal signaling. They lie along the x and the y axis, and they're equal energy, so they're equal distance. So if I wanted to use the same approach that I used earlier, the question would be, well, first of all, what would be the decision region? And so here I've traced this line here, and this would be a way to divide the entire two-dimensional space into regions. On this side of the line, I would choose this symbol. On this side of the line, I would choose the first symbol. So second side of the line, upper half of the upper section, half plane, determined by this line would be choose symbol 2, excuse me, and below that symbol 1. So if I wanted to find out what would the performance of this system be, well, it would be determined by the distance between these two. So I can calculate what is the distance between these two, just using the geometry, and I would get that the distance is equal to the square root of 2 times the energy per bit. And lo and behold, this is the same separation that I found for the on-off keying example. So I could conclude that I already know the performance and that binary frequency shift keying would have like a 3 dB penalty compared to BPSK. So the idea in binary was to look at the separation of signals, but there were only 2 signals, so there was only one separation. And we have this idea that the closer the signals were, the more errors there would be. Certainly that's a concept, but also we had the way to come up with the probability of error. So here we went from the distance to an equation for the probability of error via the Q function. That's what we learned in Chapter 3. So we'd like to do something similar when we do the expansion to M-ary signaling. So that worked for binary. What do we do for M-ary? Well, we define what's called a minimum distance because now we have many symbols. And so if I took any 2 pairs of symbols and I said, what is the difference between every possible combination of pairs of symbols? Well, among all of them, there would be some, maybe one unique one, or maybe there's a few symbols that are separated at the minimum distance. So the minimum distance is by definition, I take the distance in the signal space between any 2 symbols, I not equal to k. I calculate all these distances, I look for the one that's smallest, and I call that the minimal distance. And if I wanted to, I could define another minimal distance, which basically is normalized reference to the energy per bit. So same idea, except here this would be a function of the energy per bit, and here I normalize it by the energy per bit. So an important concept is that when we calculate these minimum distances, we have to make sure that we have the signal space normalized correctly. So remember, in normalizing, we're going to use that the energy per symbol, it's the average energy, and I just average over all the symbol energies, it's easy. And then the energy per bit is related to the energy per symbol by the number of bits per symbol log 2m. So together, this definition of the minimal distance and these definitions of the average energy per bit, energy per symbol, because of course the energy per bit comes here, so I have to make sure I have good definition. They're all given by this. So this is my idea of taking the binary case and I'm going to generalize it to M-ary with this concept of minimal distance. So now I'd like to give you a few examples in the signal space to show you why this normalization is so important, how you would do it correctly, and some observations on different kinds of constellations. So we're looking So here are some examples in signal space. The first two examples are binary, and after that I've got 4 symbols. And so I want to talk now just like how do you look at them? How do you interpret them? What should you be bringing your attention to for these different geometries? Well, the first one, let's look at this first modulation format, and we can see we would call this antipodal because we can see that they're on either side of the origin here, the symmetry to it, so that would be binary shift keying. Here we're noticing that they're orthogonal, they're at a 90-degree angle, so this would be like BFSK, binary frequency shift keying, which is an orthogonal modulation format. All the symbols are orthogonal to one another. Now I get to QPSK, and it's kind of a mismatch. I could interpret them as being antipodal, I can think of them as being at right angles, so something else is going on there. And now if I look from this modulation to the next, oh, here I'm saying that there's some that are orthogonal, that's certainly true. So now if I look at what goes on between this third and the fourth one, it's basically just a rotation. So they're still equidistant from the origin. In this case, they're forming a square, like where the units would be like plus and minus 1. And here, instead, they're right along the axes. And then in the last example, it's taking these 4 and it's kind of like translating them, moving them side to side, not rotating, but moving them side to side. These are no longer at the same distance from the origin. When I rotated them, of course, they're all equal energy, same energy. But here that's changing. Here's one at the origin, and that's clearly got 0 energy. So I said normalization is critical. So let's sort of like check the normalization. What's going on here with the normalization? How do we get it? So we'll start here with the energy symbol 1 square. The energy is the L2 norm. So the S1 squared, S2 squared, they're both equal to EB. And then clearly the average energy per bit is EB, and the minimal distance, we can read it here. Okay, so this EB, the markings on this drawing are correct. This is correctly scaled for signal space. Again, we'll do the same thing here for this orthogonal modulation format. The distance to the origin, the length of the S2 vector we can see right here. The length squared is EB. Here the length squared is EB. So they're equal energy. The energy is EB. We note that they're orthogonal. And so the average energy per bit is, of course, 1/2 of EB plus EB. So that gives us EB. And the minimal distance, by the geometry we can calculate it as being the square root of 2EB. So here we've gotten the d min on this first one and the second one. Let's figure it out what it is for this third constellation. So on this constellation, we notice that they're all equidistant from the origin, and we calculate what is their L2 norm, and we get 2 times EB. Now I have to calculate what is EB. Is it really the average energy for this bit? So this is what I am checking. Is it true? So I calculate the average energy per bit, and indeed if I take 1/4 of 2EB plus 2EB plus 2EB, I get plus 2EB, I get 2EB. And so if I divide by 2, I'm getting this representative is correct. So check off, yes. Everything makes sense here. The EB, as it is written, truly is the average energy per bit. So very self-consistent. Now I go to the rotation and the translation, and we'll see what happens in this case when I'm calculating D min with the correct normalization. So first the rotation. Now I go through the rotation and I see that I am preserving, if I look at what is the energy for each one, just like in the previous, the energy per each one of the distance to the origin was 2EB. And as I went here to the rotation, of course, it's just a rotation. The distance to the origin did not change. And so now the coordinate represents the distance to the origin, so it's again 2EB. And again, when I do my calculation, everything's really going well here. This is the correct normalization for this space. So what happens now when I look at translation? When I look at translation, say that I just take these coordinates and I just shift them up so that what was this point becomes the origin point. Well, this one, the different distance between these two was 2 the square root of EB, so I'm just going to maintain that distance. And so I would think these were the coordinates. But this is not correct. In fact, we have to renormalize because these were the correct coordinates in terms of the average energy per bit, but when we calculate the average energy per bit here, it's not going to be EB. And that means that the normalization is not correct. So translation is very important, that a new normalization take place if we ever do the translation of a constellation. For instance, if I take these coordinates as they're listed here, and I just calculate what is the average energy, it's 1/4, and then of course this one's 0 energy. These two have energy 4 EB, and then this one is 8 EB. And the average then comes to be 4 EB, and that is not equal to 2 EB. Remember, it's supposed to be EB times log 2m is equal to the average energy per symbol, but here that's not the case. So these coordinates are wrong. And what we have to do instead is change these coordinates, and these coordinates should be the square root of 2EB. And now at least we have the correct normalization for signal space. Now I can calculate what is the D min. And when I calculate the D min here, it's the square root of 2EB. So compare these two. Here is BPSK, here is QPSK, and they have the same minimum distance. But here BFSK, and now this sort of not BPSK, QPSK, this shifted translated one, now I've made my performance worse because my D min has become smaller. So you can't see it. You have to normalize it in order to see it. And really the whole point of this discussion is for you to realize to be critical and make sure that when you do an operation that you maintain the correct normalization to preserve that this is truly a signal space representation. So you might ask the question, what is the best translation? I saw that as I moved from here to here, this translation was a bad translation. Is there one that's a better one? Is there an optimal one? And indeed, the optimal translation, so if I take any modulation format, I just sort of move it, what would be the best place to move it? And it turns out that the best place to move it is to look for, if you will, the center of mass. And if you want to minimize the energy here, you would take the offset to be 1/m, the sum of the squares of SI. So think of these as being different points in space and representing different masses. And if you find the center of mass of all these points and put your constellation centered at that point, that will give you the most power efficient constellation. And so just to conclude, here are our final results, our calculation for the minimal distance for each one of these constellations. We found 3 that had the same value, the smallest, a very small minimal distance. And then we had 2 examples where the minimal distance was larger, and in this case they happen to be equal.